Hello, everyone. My name is Jeff, and I'm from MIT CCL. I will present our work on semi-supervised spoken language understanding via self-supervised speech and language model pretraining. And this is a collaboration with Amazon and National Taiwan University. So spoken language understanding is the process of extracting semantics from speech. And semantics are usually defined as intent and slot sequences. So for SOU, we can put it in the context of a social conversation system. And this is Gunrod from the Alexa Grand Challenge contest. And we can see that there are mainly two components in the SOU system. So there's the ASR, where it transcribes the speech utterance to transcript, and there's the NLU model, where it can be, for example, a BERT that parses the text transcription and returns intent and slots for the downstream task. So to put our work into context of prior work, what is missing in terms of modeling. So high performance SOU model often requires large amount of data from the same source. You can think of Alexa or Siri, but this is not always available if you want customized or low resource SOU models. And a lot of prior work are two-stage approach, but where it has an ASR model and a NOU model that's optimized separately. So that's not ideal. And a lot of the end-to-end work, prior work, only does intent prediction without predicting the slot sequences. So that's not ideal as well. For evaluation, we would desire an end-to-end evaluation metric. So in this work, we propose a slot edit point score. And we would also like our SOU model to be robust when there is environmental noises in the background. And this is just to compare our approaches with prior work in terms of input-output and in terms of evaluation metric. Our problem statement is to build a clean, working, semi-supervised framework for extracting text and semantics from speech. And we're interested in two settings. The first setting is there is only limited semantics label, but there is additional transcribed speech. So in this case, we would take advantage of a pre-trained BERT and a pre-trained ASR, and they are jointly fine-tuned for ASR and intent classification and slot filling. The second setting is that we relax the setting a bit, that there is only untranscribed speech available. So in this case, we will take advantage of unsupervised pre-trained speech and language representations. So now I'm going to proceed to our first approach, where it is basically cascading an ASR to an NLU. And the bottom here is the visualization. To implement our NLU, we went for a BERT. So this is just a standard BERT that is jointly optimized for intent classification and slot filling. And this is the results on ATIS and SIPs. And we can see that they are very good, above 95% for both metric. And this will be our top line because the Oracle text transcription is available. For the ASR model, we went for the end-to-end ASR that is based on Shinji Watanabe's work. So here we have a transformer encoder-decoder architecture that is trained with two objectives, the CTC loss and the attention loss. And each component here are pre-trained on Libre Speech 960 hours. So in summary, our two-stage approach during training, we first trained ASR, and we trained the NOU model, which is a BERT. And during decoding, we simply take the ASR top one hypothesis and input that to BERT to get the results. To evaluate our model, we propose a slot at the F1 score. And the idea is simple. We essentially loop over all the possible slots, and for each slot, we calculate the F1 score and then accumulate across slots. And this is one example on how we calculate F1 score with false positive, false negative, and true positive. So the results on ADAS, we see that at the bottom row is our proposed two-stage baseline. We see that we have a pretty strong ASR model in comparison to prior work. And this is compared to a CALDI ASR plus BERT system. And we see that we are also outperforming them by a significant margin. So now I'm going to proceed to how our end-to-end model proposed in our paper. And the main benefit of doing end-to-end training is that now the error from the semantic side can now backprop all the way through to the speech input. And we want minimal modification to the two-stage approach, as minimal as possible. And this is our proposed approach. The only modification during training we made to the two-stage approach is here, where we concatenate the attention decoder hidden representation and the BERT hidden representation to predict slot and intent. So now we have 4 losses during training, and everything is trained end-to-end. But we need to make sure that ASR and BERT usually have different tokenization methods, and we detailed how we deal with this in the paper. During decoding, similarly, we split into 2 parts. We first decode for ASR, and then we take a top one hypothesis and input that to BERT. To get the attention decoder representation, we take the decoded transcript and input that back to the attention decoder to get the corresponding hidden representation, and concatenate that with BERT to get the decoded intent and slot sequences. So this is the result on ADAS. We see that now with end-to-end approach, it outperforms the two-stage approach and of course the previous work. And it's actually on par with the NOU top line where Oracle text is available. Lastly, another key aspect of the evaluation is to test the noise robustness. So we, because SOU model often operate in an environment where environmental noises are in the background. So we adopt MS-SNSD for our as the noise template for testing our model. And I listed some of the noise types here. Some of them are more challenging. And what we did is for each clean file, we randomly sample 5 noise file and augment them with 5 levels of signal to noise ratio. And we see that a model that's only trained with clean data suffer from noise degradation. And this is true even if the model's ASR is trained with spectral augmentation. So with a simple noise augmentation training scheme, there is now minimal noise degradation. With noise on noisy test sets, our end-to-end approach can achieve 95% slot at the F1 score. We can analyze the error comparing the end-to-end approach to the two-stage approach, and we see that the red bar, which is end-to-end approach, always outperforms the blue bar. And we can do this for different signal-to-noise ratio as well. Now I have presented the end-to-end approach and the two-stage approach. Now the question is, since BERT is very powerful in on extracting semantics from text, can we somehow adapt BERT to take speech as input and outputs intent classification and slot filling? And we found speech BERT fitting for this purpose. So we're going to apply it to our setting. So this is a speech BERT setup where we pre-train the BERT with audio mask language modeling and fine-tune the BERT for intent classification and slot filling. So this is the speech BERT setup. First, we have to force align audio with this transcription. So each word token corresponds to an audio segment. During pre-training, the objective is to take the masked audio segment and predict the corresponding word transcription. During fine-tuning, we take the audio segment and predict the slot sequence correspond to those segments and the intent label. This is the results for speech BERT, and we see that it performs on par with the two-stage baseline, but still lacks the end-to-end approach a bit. Lastly, I want to describe, supervised pre-training is not always available because according to UNESCO, a lot of the language are endangered, which has little transcription. So this bears the question, how effective is unsupervised pre-training for the speech part? And we know that Wave2Vec 2 is very successful, which has achieved very low word error rate in the low resource ASR region. So what we're going to do is take the context and latent speech representations and feed those into our SVU system. So in the previous setting, we have two pre-training steps. Our BERT is unsupervised pre-trained, and our ASR is supervised pre-trained on libre speech. And then they are jointly fine-tuned on the SVU data sets. But now we only have unsupervised pre-training, so which is the Wave2Vec and BERT. During the SVU fine-tuning, we freeze the Wave2Vec, extract the Wave2Vec feature, and train an ASR decoder with BERT jointly. And in this case, we do not need additional transcribed speech in this setting. And this is the results. At the bottom row is our two-stage model with unsupervised pre-training. And we see that now with only unsupervised data available, we can get 85% slot edit F1 score, which is not too terrible compared to supervised pre-training. And this is my presentation. If you have any question, please, you can email me at coai24@mit.edu. Thank you very much.